We've just released our fireflow analysis utility for EPANET.js. This allows you to run fireflow simulations and understand the capacity for junctions in your network to supply firefighting flows. Here we can see our little demo network. In it, we can choose two parameters. We can choose our flow rate. So in this example, we want 10 liters a second from each junction. And then we can also pick our minimum pressure. In this case, we'll do 5 meters. Now, when we select calculate for all junctions, EPANET.js will run a fireflow simulation on every single junction within the network and confirm if that junction can supply the required flow rate without the pressure being reduced at that location below the minimum pressure, in this case 5 meters. If we look at each of the junctions, we can see some are green, which pass, and some are red, which mean they haven't passed. If we select a junction, we can see it's highlighted in the row down the bottom, and we're given a range of values. The first is the initial pressure. So this is the pressure before any fire flow was applied, in this case about 27 meters. The next is the fire flow available. This is the first calculation that's calculated. This tells us the maximum amount of water that we could extract at this junction before we get below 5 meters of pressure. In this case, it's saying that there is 12 liters a second of firefighting capacity. Our needed fire flow is placed here, which is the 10 liters a second that we entered here. And we can tell because the fire flow available is greater than the needed, it will pass. And we can see the second simulation that is run is the one for the needed fire flow for the 10 liters a second. And we get the residual pressure, which here is 11.446 meters. This is how much pressure would be left if you were extracting this 10 liters. And finally, we get the pass. We can also see some of these rows are highlighted with red. We select them. We can see that the junction is red. And what's highlighted is the fire flow available. We can see here that there's only 6.26 liters of fire flow available at this junction. And it's also highlighted here on the status. If, for example, the initial pressure was below the minimum, we would also get a warning saying that the initial pressure was lower than the required minimum pressure. Now, these calculations are done just at the junction where the fire flow is. So it is only looking at the flow being extracted from that point and the residual pressure at that location. You may want to confirm that you're not breaching any of these requirements in other locations within the network, in which case you can run a design fire flow. And this is a third fire flow that can run. And what it does is it will look and confirm that the minimum pressure has not been exceeded anywhere else in the network. And you can also place a maximum velocity for any of the pipes throughout the network too. In this case, we'll do 2 meters a second. We can calculate it for all of the junctions now. You can see it's run again. And this time we've now got the status has changed to design, where it has run some additional checks. So we still have the same values that we had before, the fire flow available, the fire flow needed, but now we also have a couple extra columns, some for fire flow design, the pressure, the residual pressure at the design flow, and some critical assets as well and iterations too. So if we go to one of these regular junctions, we can see that we have the values as we expect, and you can see it hasn't done any extra iterations. But if we pick this junction here, in this case, the fire flow available is too low. Let's find one where it has done a design fire flow. Here we can see here the maximum velocity is being reached in the network. We can see that while the available fire flow is 13, and that would meet our 10 meters needed fire flow, which would also stay above the residual pressure requirement of 5. We can see that we have a design flow of 6 liters a second with a design pressure of 11.96. So this is the minimum pressure throughout the network. It's still above that required, but we can see pipe number 5 has a velocity restriction. We can actually go in and see the iterations it goes through to calculate this. And we can see here that this P5 is now running at 2 meters a second. So with this, we can be confident that even though it says the hydrogen is capable of extracting this amount, there is actually other elements within the network that have a restriction. We provide 2 demo models with the fireflow utility, and you can test out the application with those. However, it is possible to load your own network. All you need to do is drag and drop the IMP file, so this is your EPANET model, into the application. And now you have your own network projected on the map, and you can run your own analysis. In this case, the network is quite larger, and it also has an extended period simulation. So you can pick the peak hour or when you would like the simulation to run, and then once again, choose the parameters that make sense for you. I'll just bring these ones down lower, and we can run the simulation. This simulation is a bit larger, so it will take a little bit more time to run. You can see it's going through the simulations itself and slowly working through them. We can see we're running through about 300 or so simulations per second. It doesn't take too long to go through all 6,000 simulations. Here we can see a range of simulation results, the green passing and the red failing. Hope you like this application. You can access it now on our utilities website of EPANET.js. Please let us know how you're using it. We think this is the next stage of simulation types within EPANET.js, and eventually we'll bring this directly into EPANET.js itself. Thank you so much.